All right, you guys ready to go through this application problem? Bless you. So there's kind of a part of rectangles where it's like, okay, Miss Noah, but there's got to be like a better way. Yes, there's a better way, but rectangles is like the first step in just understanding how to divide up space and get area. And you get to a problem like this, and even though it's a book problem, it's actually a pretty good, it's not a stretch to say that this is a pretty good reason to understand a rectangle method, because the bottom line is number 11, you can't do it another way. It's like a data problem. And when you have data, you'll find out that the only choice you have is to divide up into rectangles and then to deal with each of those. So it's a good problem. What do we got? We've got some water. It says it's like a tide or tidal area, tidal river, but you basically have some velocities. And that should catch your attention. Okay, we've got these velocities. Yesterday we talked about that the area under a velocity graph. Well, stop right there. That's exactly what we're going to do. We're going to make a velocity graph. Okay, now of course, once we make this velocity graph, we're going to find the area under it. And ultimately, that's going to end up being the answer to our question. The question really is, how far does something go? How far does the bottle go? The question is really, what's the distance traveled? Okay, now it's actually a problem that does require like a sketch. Like, we're not just going to be able to put some numbers in our calculator. But as you're going to see, I hope that I'm going to make an abbreviated sketch. I hope that it doesn't confuse you that my abbreviated sketch is actually to save us a little bit of time. But we're going to sketch some velocities. So we'll start it at 0. Obviously, the data that they give, and that well, it's a velocity of 1. It says 1 meter per second. By the way, there's a little issue here with minutes and seconds. We'll figure that out, but right now we can just graph kind of what we're given. So then I'll go to 5 minutes, and it says 1.2. Okay, again, it's just a sketch, but 1.2 is going to be a little higher. All right, so don't worry, we're not going to graph all of these. I said we're going to make an abbreviated sketch, but you have to understand what's going on so that the abbreviated sketch doesn't confuse you. All right, so I graphed 10 minutes at 1.7, and I graphed 15 minutes at 2.0. Okay, now there's many more velocities at 20, 25, 30, 35, 40. I'm going to pick it up at 45. In case you're wondering, there's still space in that ... region. There's still a velocity graph. I just feel like that the students that you are, that we could pick up on what's going on by just graphing the first few and the last few. Okay. I'm graphing the first few and the last few data points. And so I graph 55 at 1.2, and then I graph 60 at 0. I can label that. So we have the old velocity graph. Well, that is if we connect the dots. It's funny, when you connect the dots, it starts to look like area. So I connect them with a squiggly line just because we don't really know, and it's not a big deal. I just want you to realize we don't really know what the data is other than these points, but we don't have to know. We don't have to know because this is enough information for us to now do an Lram. If you look at the directions carefully, it says do an Lram. Of course, that's the left-hand rectangle approximation method. So check this out. It's kind of neat. If I go to the left side of my first interval, that would be at 0. If I go up and meet the data point, I meet a data point, that would be at 1. And I'm able to draw my first rectangle, which, by the way, I have all I need to get the area of that rectangle. The next left-hand rectangle, I go to 5. I go up and meet the graph. I go up and meet 1.2. Another left-hand rectangle. Okay, now with the data that I put on the board, I'm able to draw 3 rectangles. Okay, and nothing wrong with that. There are other rectangles inside of here. This is the part that people miss. I'm trying to save you some time, but there's other rectangles in here. I'll show you how we can pick that up. Let's finish the last few. Now, it's sometimes when you draw them on the outside that it's a little harder for kids. You see how I did that? I went to the left side. That means I'm at 45. I go up and meet 1.8. But yeah, I got to draw my rectangle to the outside. I got to draw my next one to the outside. Each one of those rectangles is on the left of the interval. It's on the left of the interval. All right, now region 1, 2, 3. And if you did a little bit of math, you would say there actually were going to be 12 regions. So we've got 10, 11, 12. So we've got rectangle 1, 2, 3, 10, 11, 12. And we're ready to find the Lram. Okay, now as you do this Lram, just like we've done many times, you're going to multiply the width, which is 5 minutes, but the width is 5, times the height. Well, for the first one, it's 1, 0. And 5 times 1, 2. 5 times 1, 7. Now, we might be getting closer to a point where you catch on to a little shortcut. I'm being honest, we're getting to that point. That's the whole point behind this. But I'm going to write some stuff out. Usually, before we understand a shortcut, we got to realize the theory. So each one of these rectangles over here is a 5 by 1/8, 5 by 1/5, 5 by 1.2. Just worth noting, I didn't use the last data point. I didn't use the last data point, but I did use the first data point. You see how when you're on the left, you do encounter the first point, but you don't encounter the last. Just keep that in your back pocket. Don't I need to add all of these together? Okay, it's sort of like, yes, right? I need to add all these. But what am I really going to be adding? What am I really going to be adding? Well, velocities. Because every velocity is just getting multiplied by 5. Now, if you look in your book, you have all the velocities. Again, what am I really going to be adding? The velocities. Okay, now, they're even the ones that are not up here. They still count. So, you add up all the velocities. Now, I did this ahead of time, but you should kind of just notice that, geez, if you add up those numbers, 1, 1.2, 1.7, 2, ... If you add up all the velocities, it only comes out to be 17.4. Make sure you're not surprised by that number 17.4. Because we're going to take that sum, and then we can just multiply it by 5. You can just do that in one step. Okay, I don't need to multiply everything by 5. I can just add them all up and then multiply by 5. And that gives us our total distance, which should make a little bit more sense, sort of. The reason I say sort of is because we've got an issue here with minutes and seconds. It comes out to 87. Now you might wonder, 87, oh, meters. Okay, yeah, 87 meters. But, well, there's an issue here, and that is that these velocities were in minutes. They were in, I'm sorry, these velocities were in seconds, but my interval is in minutes. And so we can do a simple conversion, which is basically how many minutes, how many seconds in a minute, and it'll fix it. We can multiply it by 60. Okay, instead of multiplying every number by 60, we just do it at the last step. So it's 5,220 meters, which is quite a bit, but there must have been a lot of movement. There must have been a lot of movement for this bottle. Now, that's the left ram. This is the part where you kind of have to make a decision. You have to make a decision if you're going to keep paying attention. I hope you do. I also hope that you realize that there is a shortcut to this. But I want to show you. I want you to see the shortcut. Okay? And that's why we're making a little graph. Okay? I know it kind of seems like, oh man, you're doing this again. Well, yeah, kind of. I am doing it again. Some people will do it on top of this one. I am not going to be that person because I don't want to confuse you, but you could maybe be that person. So, da-dee-dee-da-dee-da, we're going to graph some of the points. Okay, again, I'm graphing just kind of the first few and the last few. Careful, I hope you're not saying, well, it's just going to be the same answer. But are you wondering about the answer? But I hope you're not saying it's just going to be the same. That's really the whole point behind this, for you to realize that it's actually going to be a little different. A little different. All right, so don't forget what's going on here. We're making a velocity graph. That is important. We're making a velocity graph. Yesterday, we discovered with that simple train problem that the area under a velocity graph is distance traveled. It's the same premise here. The area under a velocity graph. Right ram. Right ram. I want to encourage you to think about drawing a rectangle. I'm going to have you do it in an exit ticket in a moment. And I say that because sometimes kids are like, when they actually have to do it without seeing me do it, you're like, uh-oh. You know, how am I supposed to draw this? So if you just want to think about drawing a rectangle, I'm going to draw the first one between 0 and 5. It's not the same one that got drawn over here. If you want to watch, I go to the right side of the interval. So I go over to 5. When I go over to 5, I go up and meet the function. And you got to square off your rectangle. So that rectangle's on the right. Whoops. I did that backwards, right? Good. I'm glad you're paying attention. It seemed strange to me too, honestly, but I still did it. So I need to go to the right and meet the function. So I'm going up here to 1.5. I'm going up here to 1.2, and I'm not going anywhere. Okay? Rectangle 1, rectangle 2, rectangle 3, dot, 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 rectangle 10, rectangle 10, rectangle 11, technically rectangle 12, but it doesn't have an area. They're all 5 bys. Not 5 guys, but 5 bys. So it's 5 by 1.2. It's 5 by 1.7. It's 5 by 2.0. Maybe you're just kind of copying some numbers. I hope that class is more than that. I hope you're thinking, because right now we can see that these two answers, well, they actually involve different numbers. They actually involve different numbers. Or maybe we could say that they really just involve one different number. Now that takes some processing about what the whole big idea is here. Please make sure you understand, and this is every year I kind of like, should I do this differently? But it's not just 6 areas. There's all the area in here also. You have to add that. So I showed the first 3 and the last 3, but you have to understand that what we're really doing is adding up all the y values. And here's where we can make this simple observation. Which y values am I using? If it's on the right, then I'm actually using the far right y value. I'm using it, but I leave out the one on the left. And it's the opposite over here. When it's on the left, I use that y value, but I leave out the one that's on the right. Every other number is the same. So the sum of the velocities, aka the sum of these y values, okay, it's actually going to just come up a little bit less. Because if you notice, 1.2 is my last one here, but 0 is my last one here. I'm going to come up 1.2 less. Let me just make sure I'm getting the right number, but that's why it comes out to be 16.4. 16 point, wait a minute, 16 point, I kind of point at the wrong number. It's this number that's not being used. My bad, I kind of pointed at this number, but that was not right. It's this one that's not being used over here. That's why it comes out 1 less. It comes out 1 less. Okay, we're still going to multiply this by 5 because every rectangle has a width of 5, and that gives us our distance, or total distance. So we take 16.4 times 5, you end up with 82. But it's got this like minutes, seconds issue, so we multiply it by 60, and we end up with 4920. 4920. So, how far did the bottle go? Well, we have 2 estimation techniques, and so we could give our best approximation by obviously doing something with these 2 numbers, that is averaging them. And I erased the 1, but it was 5220. This one again is at 4920. And we'll divide that by 2. It'll give us our best approximation of 5070 meters. It's not supposed to be a stretch. It is a practical use of rectangles, because all you need is the y values. All you need is the dimension, the height of them. And if you observe, I can go to the left or the right and end up with some decent areas which represent the distance traveled. All right. I, as we do sometimes, try to sort of force you guys to, figure some things out. And that's with this little guy. Now, take a look at it. I can get you some scrap paper if you want. If for some reason you'd rather use your own paper, it's fine. But Notice that I'm having you draw, because this is like the skill that you need to get from this section. I'm having you draw the left ram, but I want you to use the calculator programs for the remaining rams. So it's a good summary problem. Kind of puts together this first section.